This truck has a 13-litre, 410 horsepower engine, and it runs on this very special fuel. And I can also run on this fuel. This is vegetable oil. Don't do it with diesel. It's not diesel. Our bodies and engines run on similar fuels, but food is much more than just an energy source. It's also our construction material. It's what we make ourselves of. And I'm going to show you how. Welcome to the Christmas lectures from the Royal Institution, supported by CGI. I am Chris Van Tulleken, and in lecture 1, I talked about how your gastrointestinal tracts destroy your food down to its nutrients and you absorb those nutrients. Now, in this lecture 2, we're going to look at the fate of the nutrients inside your bodies, both as fuel and as construction material. But first of all, let's look at food, the food we eat, as fuel, as an energy source for our body. Because that vegetable oil that you saw me drink downstairs, diesel fuel, petrol, and this bag of potentially explosive chemical energy, chemical fuel, don't bring it too close to me, stay there. They're all very similar forms of chemical energy. Now, I need a volunteer. How about you there? Yes, in the grey. Yeah, come on down. Come on down. Very nice. Here, turn and face the audience. Now, what's your name?
Dora.
Actually, you know what? I don't think I want to get to know you too well, Dora. I don't think we want to form any kind of emotional bond. You are going to put on this protective equipment, and you are going to take that bag of potentially explosive chemical energy up to the roof. That's good. Get the visor on. There. Not that it's going to do much good if anything goes wrong. This is really just for the look of the thing. OK? Good. Now, and Dora, can you stand between me and the bag? That's great. That's great. I mean, you're a sort of blast shield. I'm going to stand over here. OK, you've got it. Dora, hurry up, fast as you can, up to Dan, waving up there. Not too fast. Tuck your legs in, everyone. Lean away. That's good. Up you go. That's good. Quickly. Quickly. Not too quickly. And we're all safe. Great. Now, as that special fuel makes its way to the roof, we've seen lots of different engines so far. You've seen that truck engine. You've seen the little engine in my motorbike. I now want to show you another kind of engine. This is a steam engine. And the engine you're about to see was actually built by my father. And it was built using kits, toy kits, from when he was a boy in the 1950s. That's great, and here it is. This is a steam engine, and this is, of course, my actual dad. Hi, Dad, how you doing?
Hi, Chris.
It's running really well. What are you running it on, though?
Chocolate. And it needs a little pep up here.
Need a little pep
touch
up.
of a pep up. Yeah, we'll
Keep it going. Can you show us the little tray? Oh, yeah, it's oozing.
Here's the tray with the chocolate.
There's a bit of... OK, there's flaming
the
chocolate in the tray.
Chocolate's gobbing it up. Yeah, there we are.
And how's that working?
The steam engine works by a fire underneath, steam in the boiler under pressure. The steam comes into the piston here and keeps...
And it keeps spinning. It's going to keep going. It's going to keep going.
That's right. It'll keep going.
And it's running on this kind of
It's
chocolate.
running on chocolate.
So it's functioning as cold. Now, this kind of chocolate, this is perfectly edible chocolate. You can run my body, or either of our bodies, on about 4 bars of this chocolate per day. It will give you the energy you need, but not many of the other nutrients that you need. And a bar of chocolate like this has around 500 calories. And when we say calories, we really mean kilocalories. And a kilocalorie is the amount of energy that it takes to heat up 1 litre of water by 1 degree Celsius. So if you used a bar of chocolate like this, you could bring a pan of water that size from near freezing point to boiling point using just that bar of chocolate. There is a massive amount of energy in chocolate. Now, the human body's pretty efficient. How about the efficiency of the steam engine?
You're losing a lot of energy here and a lot of heat. The steam, everything else. It's just not a very efficient way to run a motor, but it's doing its best.
There's heat, there's smoke, there's steam, there's chocolate on my hands. I'm going to put that down.
Yeah, that's right.
And you spent your life as an industrial designer, as an engineer, and so you understand about efficiency, and this is not an efficient way. We actually did some calculations, Dad. If my body was as inefficient as a steam engine, I would need to eat about 40 bars of chocolate a day. Well, that amount of energy.
Yeah.
Thank you very much for that. Thank you so much.
Cheers.
Thank you.
Oh,
And I'll let that go. So we've seen food being used as fuel in 2 different kinds of engine, but what do foods and the fuels we run our internal combustion engines on, what do they have in common? Well, to find out, we're going to head to Jason, who is on the roof. Jason, are you there?
Hello, Chris. Yes, I can hear you loud and clear.
Brilliant. Has the volunteer arrived?
Yes, the volunteer has just arrived.
That's great. We'll stand well back, Jason. We can't afford to lose you. You're a valuable member of the demonstration team.
Why, Chris? This is just icing sugar.
Is it? I
Yeah.
thought it was. I thought we were doing something dangerous.
Absolutely we are. But
I've
it's just
become
icing sugar.
confused. Sorry, Jason. So what are you going to do with the icing sugar?
Well, I'm going to pour it into this beaker and I'm going to mix it with some highly concentrated sulfuric acid.
Okay, and is that a safe thing to do?
What do you think? Look at me. I'm wearing all this safety gear.
Okay, I know what's happened. I've got confused between icing sugar and concentrated sulfuric acid. Now, if you are baking at home, you must not confuse
Chris, I'm just going to have to
two-
interrupt you there. You're wasting time. Can we just
Sorry,
get on with
Jason.
it?
Yeah, okay, let's get on with it.
And I'm getting the sulfuric acid and I'm going to pour it into the beaker, as you can see. I'm going to give it a nice stir. It's going black.
There's a bit of
And I'm gonna
something
walk
coming
away.
off. Whoa. Okay, so this is a spectacular and very visual, vigorous, fast chemical reaction. And it's revealing something about the fuel, isn't it? What are the elements that you can see? In fact, Jason, can you send a volunteer back down with some of the sample so we can actually see it? Because that worked brilliantly well.
Absolutely, Chris.
Brilliant. Thank you, Jason. What elements can you see in that reaction? Who thinks they can name one of the elements that's going on? Put your hand up if you think you can name an element. What do you reckon? Steam, brilliant. Now, do you know the elements that are in steam? What atoms are in steam?
It's water and air.
Water and mixed with air, that's right, steam is in the air. And in the water, we've got hydrogen and oxygen, haven't we? What's the other element that we've revealed very clearly there? There's a 4th element, yeah. Carbon, right, that's the black stuff we see coming out of the tube. The sulfuric acid dehydrates the sugar, it grabs the oxygens and hydrogens off, and all you're left with is raw carbon. There's also some sulfur dioxide, which is the foul-smelling, very slightly poisonous gas that makes volcanoes stink, and that's why we did it on the roof. Now, while the volunteer's coming down, I want to show you the special thing about carbon. Because carbon, hydrogen and oxygen are the 3 main elements, the atoms, the different atoms that we're going to be talking about today. And there's something here we go. I'm glad we got Dora's name in the end. She survived the ordeal. Big round of applause for Dora. Great work. Now turn around, Dora. Turn around, Dora. And actually, can I lift up your visor? We can take your visor off. We've overdressed you. I'm going to put it with your ticket. This is a carbon snake that we made earlier, and we've washed it for many hours, so there's no more acid on it. Tell us what that feels like. Lift it up. Lift it up. Is it heavy?
No.
Would you say it's strong, or is it quite crumbly and fragile?
Crumbly and fragile.
Quite crumbly and fragile. Dora, you have done a brilliant job. That is raw carbon. I would give it to you as a souvenir, but although we've washed it, the middle of it is probably still full of concentrated sulfuric acid. So we're not going to do that. But a big round of applause for Dora. Leave it back in the thing. So this is raw carbon. It's quite an unremarkable substance. It's quite fragile. It's almost exactly the same as the lead in your pencils. That's pure carbon. But let me show you the special thing about carbon. I've got two molecules here. These are glucose molecules. They're made of just those three atoms: carbon and hydrogen and oxygen. And if you look at the carbons, you can see the special thing is that each carbon atom can bond to 4 other atoms. And what that means is carbon can form a chain, as it's done here in this glucose, but then it can also have oxygens and hydrogens or other atoms poking off the side that change the properties of the carbon. Now, we can join these two glucose molecules together, and we start to make starches, the kind of starches that you eat and break down in your gut. If you were to give me another kind of atom, if you gave me some nitrogen, I could rearrange just these then 4 elements and make amino acids, the building blocks of proteins. And proteins are the complicated molecules that really make you, you. If you then gave me some phosphorus, I could make DNA, okay? So carbon is the basis for all of the important molecules inside your body. It's how we make big, complicated molecules. And it's 12% of the atoms in your body are carbon. But where does all the carbon in your bodies come from? All the carbon atoms in your body, almost without exception, have come from plants. Now, some of them may have gone through an animal first, but they all come from plants. What this plant is doing is taking in carbon dioxide from the atmosphere, and it then uses the sun's energy or energy from the lights in the theatre to make complex molecules, molecules that we can live on. And most importantly, plants make our fuel. And we call the molecules that we can get energy from macronutrients. And there are 3 main ones: fat, protein, and carbohydrate. They all come from plants. And they contain very different amounts of energy. So when we talk about energy, we do talk about kilocalories, and we say that proteins and carbohydrates produce around 4,000 kilocalories per kilogram, but fat has far, far more energy, almost twice as much energy, around 8,000 kilocalories per kilogram. Now, to demonstrate just how much energy there is in fat, I have asked Dan from the demonstration team to prepare a chip pan fire as a way of showing just how much energy there is in fat. Here he is. Dan, I'm expecting this to be pretty spectacular.
It's gonna be good.
Chip pan fires, of course, are very dangerous, so there's a health and safety element to this demo as well. OK, Dan, I want this to be big.
Of course.
It's the first really big demo we've got going.
I'm excited.
Set up the chip pan.
OK, so first of all, we need my chip pan.
What's that?
It's my chip pan.
That's not a chip pan. You can get 1 chip in there.
Yeah, but I think this will be good enough.
Dan, this is really embarrassing. This is my lectures. Why are you doing this? I wanted a proper chip. All right.
I really think this will be good enough.
OK, Dan has prepared the world's smallest chip pan fire. We're all going to have to use our imaginations here to see how this works. OK, Dan, well, tell us what you're going to do.
So I've got some oil.
Great.
I'm going to put some oil in my chip pan.
I mean, this is hopeless. I'm so sorry, everyone. I'm embarrassed. This isn't how I wanted my second lecture to be going, but just, sorry, Dan, get on with it. Get on with it.
Got obviously some
All
PPE.
right. So you put a small amount in and...
Yeah, look at all that.
Yeah, that's looking great. OK, what are you going to do? Set it on fire?
I am going to heat it up, but you are going to want to back up.
Why? What, like here?
Further
Dan,
than
there's hardly any... All right, I'll go and stand over here.
Come on.
I'll humour him.
OK.
An abundance of caution. Safety Dan, they call him.
OK. I'm going to heat the oil up.
Great.
I'm going to get it smoking and see if we can set it alight.
Great. OK, well done, Dan. Chip pan fire. Look, I mean, there's not much oil, but the point is this would burn for a long time. There is a lot of energy in oil. OK, Dan.
Sorry,
good.
can I just... Quick question. How would you put that fire out?
We use water to put out fire, so you just put some water on it. That's how you put out a chip pan
Can I show you what happens if I put water on there?
Go for it.
OK.
Great. Now we're demonstrating how to put out a very small fire. So you want me to stand back again, I guess?
You're
to
gonna-
watch the
you're
fire
gonna
go
do it
out.
first then. Right. 3, 2,
2, 1. Whoa!
You shouldn't have doubted me.
I should never have doubted
Never
you.
doubted
Tell
me.
us what happened, Dan. So that was very spectacular.
It was, right? So water is denser than oil, which means the water I put in sank to the bottom of the oil.
Right, like
But
in a dressing.
Exactly, yeah. Right? But the oil is way over 200 degrees Celsius, so that water boiled really quickly. Steam went up into the air, and every little bit of steam carried up a bit of oil with it, mixing with the air and the oxygen that's in it, and so we released almost all of the energy in there in one go.
And so we probably had less than 50 kilocalories of oil in the pan, but you see a very, very large flame. And there is a really important bit of health and safety here. You do not put out chip pan fires with water for that reason. Use a fire blanket or an appropriate extinguisher.
Absolutely.
OK? Dan, thank you very much. Brilliant demo. So we've burned some fuel in oxygen, we've done it in the engines, we did it in the steam engine, we've just done it with the chip pan fire. But what is happening down at an atomic level when we burn things in oxygen, when we burn fuel? Well, to demonstrate, I want to shrink you all down to the size of atoms, and I'm going to turn the lecture theatre into the combustion chamber of an internal combustion engine. Now, I'm going to need some fuel. I need 4 carbon atoms. From here, I think you've got your hats, haven't you? Brilliant. OK, come into the combustion chamber. You are about to be burned. Great. Carbon 1, what's your name?
Alice.
Alice, great. Come and stand about here, Alice. That's perfect. What's your name?
Charlie.
Charlie, great to meet you, Charlie.
Toby.
Alice, Charlie, Toby.
Monty.
Monty, great. Now, you guys, you're in a carbon chain, so you've got a bond between you. Do you mind linking arms? Like that? Perfect. So what we've got here, it could be some vegetable fat. There'd be some hydrogens off the side. We're not going to worry about that. Could be some diesel. We could put them in a ring and make petrol, sugar. It doesn't really matter. We've got a hydrocarbon fuel here, and we're in the cylinder. Now, what do we need to burn the fuel? Oxygen. Great. So I need some oxygen atoms. Can you come and line up on the stairs? Brilliant. What are your names?
Dylan. I'm Thomas.
Dylan and Thomas. Dylan and Thomas. Oh, that's. Are you friends, or is that? It's just worked like that. Amazing. Great to meet you, Dylan and Thomas. So, what we have here is a fairly happy situation. The carbons. Do you mind linking arms? No, it's fine. You guys are okay together, and the oxygens are okay together. But what would be much better? What the carbon really wants is to go and be pals with the oxygen. That would be a much more stable situation. Carbon in an oxygen atmosphere really wants to be carbon dioxide and form a very stable bond, OK? But there is a problem. You're already attached to these carbons. So we have to supply a little bit of energy to break this bond. It could be the spark plug, could be heat or pressure, and I'm going to chop you guys apart. Now, Alice, we've got you as a free carbon atom, and we need to release the bond energy. Now, when I say, you are going to go between Dylan and Thomas and link arms with both of them. Are you ready to form the bond? In 3, 2, 1, go. Link arms. There we go. And that is when the energy is released. It took a little bit of energy to break this bond, but in making that very stable bond, we released a lot of energy. You are now carbon dioxide. You are a waste gas. You are going to go out the exhaust and pollute the planet. Get out of here. We don't want you anymore. Thank you. Now, in the cylinder, of course, this is happening the whole time. OK, it's happening with great frequency. So we need to chop the next carbon. Go, stand between the oxygens. And when I say we're going to go 3, 2, 1, form the bond. Great work. And we have more carbon dioxide. Go and cause global warming. Out you go. Next pair of oxygens. Down there. OK, chop the final carbon bond. Go and stand between them. 3, 2, 1, go. Great. Carbon dioxide, you're going to go and cause a climate catastrophe. Acidify the oceans. There you go. Now, we're left with a single, solitary carbon atom. There's no oxygen to burn you. And I'm sorry about that. That happens in cylinders. So you are now a particle of soot, OK? And you're not going to cause global warming. You're going to go and cause lung disease. So what could be more Christmassy than a lump of real... This is real coal. You've got to hold it and your hands are going to be filthy. A real lump of coal from the Royal Institution. Out you go. Go and cause all kinds of lung disease on the streets of London. Big round of applause. And you can all come back and go to your seats. You understand now how energy is released when we burn fuel in oxygen, but that's no way to power a living organism, is it? Flame, soot, huge quantities of heat, noise and smoke. We can't do that inside our cells. So to understand what does happen inside our cells, I want to turn the theatre now into a cell and welcome our biochemistry expert to help me explain this, in fact, to explain it to me, Dr. Kat Arney. Thanks for coming, Kat. Now, Kat, I hope you don't mind. I've prepared your first slide for you. Some pretty straightforward metabolic pathways. Now, I'm going to be honest. As you go through your science careers, biology A-level, some of you might do biosciences, you meet these pathways. They are quite intimidating. Kat, I reckoned if I gave you a couple of hours, could you get us right through to the end in as much detail as you can?
Well, I don't know about all of you, but I've got a train to catch, so I can boil all of this down into 4 simple principles.
Whoa,
okay.
Why did no one do this at medical school? OK, go for it.
So we're starting at the beginning from those hydrocarbons, the carbon molecules, these rings and strings, and what we have to do is burn them, but in a very, very controlled way. All of metabolism is just about control. So very, very controlled burning of these sugars. Then we release a bit of useful energy. We release some byproducts like carbon dioxide, like water, like a bit of heat, just like that engine. And then, and this is the really useful bit, high energy electrons. That's what we want.
OK, so this stuff, the main output we care about, and I'm guessing it's something to do with this demonstration, is high energy electrons.
High energy electrons.
And are they just whizzing around the cell on their own?
No, that's far too risky. No, they're being carried around by these carrier molecules called NAD. So we have to carry these electrons to where we can then use that energy to turn into a form of energy that can power our cells.
Now, Kat, would you like some high energy electrons?
I certainly would.
Okay, I think we have some here. I need 16 high energy electrons. The pairs on the outside of this row, and I need to send all of you high energy electrons to go and queue up those stairs there. Would that work, Kat?
Yeah. So let's get all of them down, and then I'll tell you about where we are.
Don't knock that over. Great, and go and queue up the stairs. Brilliant work. Brilliant work. That's good. And form a queue, and we kind of stack them up as if they've got high energy. You see what I did there?
So very energetic. But before we do that, I just need to set the scene a little bit. So Chris turned this lecture theatre into a cell. But where the energy is generated is in a very, very special part of the cell. So if we can just get a little picture up, please. So what we're talking about is these little cellular power factories. Now, they look a bit like jelly beans, but these are called mitochondria. And you have loads and loads and loads of these inside every cell, and they're very, very, very tiny. But the important thing that we need to know to make energy is that, like all things inside our cells, they're made of membranes. So we have outer membrane there, and we have the inner membranes here. And on all these inner membranes, there are some pumps. And that's what we're modelling here. We have some pumps. And what these are doing is basically, like you would use electricity to power a pump and store something up, we're going to use our high energy electrons to power our pumps and store up some energy in a form that we can use. Okay. How about that?
So these pumps that we're seeing here, we're on the inside membrane of the mitochondria. We've had controlled burning of food, of, let's say, a glucose molecule. Carbon dioxide's been released, but we've now got high energy electrons being delivered into this system of pumps. Okay.
Absolutely, yeah. So then we're going to turn it into a form of energy that we can then release again in a very controlled way. So, you feeling energetic, my electrons?
Yeah.
Right. Chris, I'm going to show you what you need to do.
Can I be the first electron?
Yes, absolutely.
Sorry to barge in.
So
I want to go with the pumps.
So basically, we're going to kind of roll down. It's a gradient. So we're going to go through on a gradient. And you really want to get to here because there is something very, very special.
What's at the end of the pumps? Why are the electrons flowing?
You will find out, but you're going to want it.
OK.
OK, so what you need to do, turn on this pump.
OK, I've grabbed the first pump.
Yeah. Second pump. Come on. Third pump. Fourth pump. Woohoo! And your reward for this is what I tell you, it's what you really want. It's 1 molecule of oxygen. And 2 molecules of hydrogen.
So the electron, so H2O
Makes.
plus the electron, I've made water, and this is the oxygen we breathe, dragging those electrons across.
And making
I love
water.
It.
And so
Okay.
there, you're now,
put them
you've
back.
expended all your energy, and off you can go. So, ready? Steady? Here we go.
It's good. Give it a good pump. That's great.
Next one,
Come
next
through.
one, next
keep,
one.
keep going. Give it a good old pump.
Okay.
That's great.
All right,
Squeeze
here we
all
go.
the pumps.
Couple of hydrogens. Oh,
That's great. Keep them running. I wanted to go through
You've
twice. Oh, I
already
don't
had
get an
some.
oxygen. Oh, no, I do. I get one. OK, so I can see what's happened here, Kat.
I know you can.
We've used pumps to fill something. Now, what's gone in there? This is now a space in the mitochondria.
Exactly. And that is now full of protons. And protons are charged hydrogen atoms, ions. So they're basically like it's
So
a
they're
big...
subatomic particles, but they're the nuclei of hydrogen atoms.
And they are really charged. So this
And
is
they're,
really
they're positively charged.
They're positively charged. This is effectively a store of electrical energy.
OK.
OK, and that is there, but, you know, it's an incredible amount. You
And
might not think it's
positive
very much.
charges don't want to be together, so they're trying to get out.
They're trying to get
Now,
out.
Presumably, it's a pretty trivial amount of electrical charge. You know, this is happening inside cells. It's small.
Well, you would think that, but if you actually scale that up, it would be the equivalent of 30 million volts. OK, like that's a bolt of lightning. So this is a significant amount of electricity.
Now, Kat, if only we had a way of demonstrating a significant amount of electricity.
Well, if only we did, and I've always wanted to say this, bring on the Tesla coil.
Wow, and the Tesla coil has come with...
Thank you. This is with Professor David Ricketts from Harvard University.
Very good to see you, David.
good to
Can
see
you
you.
talk us through it?
Sure. So the electronics here are going to create a huge electromagnetic field in this coil. And it's going to resonate up, and it's going to come out as a giant spark right there.
Amazing.
And so now, which one of you want to get electrocuted?
She does.
It's your show.
All right.
OK, I'm going to do this.
Put on the glove. Or so just point at the little tip.
OK, I'm
And
just
we'll
going to
see.
point there.
I'm just going to step back
OK.
a little further. No, not you. You stay close.
No.
Are you ready?
No. Oh, wow. Whoa! That is amazing. Ah! No. I cannot feel a thing. That is fantastic. Look, it was good. It was fine, but I mean, can't you do anything bigger?
Do you want a bigger spark?
Great.
Let's
I
do
knew
it.
I could egg you on. Now, I'm going to retire to a safe distance over here. And David, before you go, how many volts is this producing roughly?
So this is producing almost 1 million volts at its maximum power.
OK, fantastic. Professor David Ricketts, thank you so much.
Nice.
So, Kat, Professor Ricketts said it's producing almost 1 million, but you said in the mitochondria we have a charge of 30 million volts per metre, so a massive amount of
It's
energy.
zappy.
So I get, it's cool, we've got a store of electrical charge here, but how do we turn that into life?
Well, you can't obviously just like shoot it out like a bolt of lightning into your cells. So what we have to do is convert all that potential electrical energy into a form that we can use. And so what our cells use are basically like kind of tiny batteries. They're called ATP. So we take some of that electricity, put it into ATP effectively, and that can then go around and do all the jobs in our cells that our cells need. So basically, ATP makes proteins do things. It makes them move, it makes them change things. It's the batteries that power all the proteins in our cells.
Do you think we could turn some people into some proteins?
I reckon.
See if we could get them to move?
I reckon. How about you three in the front row? Do you feel like being proteins? Yeah, brilliant. Okay, you're going to be muscle protein. Maybe you're going to be a motor protein, moving things around. You can be an enzyme. You transform things. So, hands in the air. When ATP hits you, you're going to do a little motion, right? Okay, so I'm going to
Kat, what have I got here? I've got...
That's some bubble mixture.
Okay.
That we're going to make bubbles of ATP. When a bubble hits you, you move. So
the
let's
protons
start.
are going to flow out. You're going to allow the protons to flow out, and they're going through something that makes ATP.
Okay, when the bubble
There
hits
we
you,
go.
hands up in the air, do the move.
There we go.
Yeah,
there we go. Great.
Now, if you just scale that up to the millions and millions of proteins in all the cells of your body, you actually turn over your own body weight in ATP every single day.
So a massive amount.
Yeah, huge amount. So just imagine that, but like lots and lots of it. And that is life. That is life in your cells.
Could you demonstrate that a little bit bigger?
I reckon we could.
Let's turn the middle section into proteins. You're all kind of different proteins. Put your hands over on the left, like that. And when a bubble hits you, you're going to wiggle back over to the right.
Bubble hits, you move. So this is ATP making proteins move and making you alive.
I think people have understood something very, very fundamental about what life is and how it works. Kat, that was a spectacular demonstration. Thank you so much for explaining something so complicated so beautifully. There is a saying in biochemistry that life is nothing more than an electron looking for a place to rest. And in our bodies, that place is oxygen. So we turned you all into different proteins, but where do those proteins come from? And all of our tissues, where does it actually come from? Well, of course, we're made of what we eat. The difference between all of you today and when you were a baby is simply a huge number of meals. So in order to see exactly what we are made of, I need a volunteer, a very willing volunteer. Okay, young person there with the lanyard. Yes, yes, great. Good, big round of applause. Come on now, stand here. Now, what's your name?
Veer.
Veer.
Yeah.
Are you having a good show, Veer?
Yes.
What was your best bit so far?
The bit where you did the confetti.
Oh, you like the
Yeah, that
confetti?
was
Yeah,
very
I enjoyed
fun.
that. They have a.
You scared me.
A good pop. Okay. We've got to get on with the experiment. I want you to come over here because what we're gonna. It's been nice getting to know Veer, but it's going to be a short encounter because Veer, what you volunteered for is to be entirely deconstructed down into your molecular components, and then we're actually going to break some of those molecules up into their individual atoms using our human deconstruction machine, okay? So a farewell, adieu to Veer. In you go to the deconstruction machine. Bye-bye, we will miss you. It's been great getting to know you. He seemed like such a nice chap, didn't he? Now, are you ready? Go. 5, 4, 3, 2, 1. I think he's ready. There we go. Okay, let me just pull out. And what we have here, look, here he is, including his little lanyard. The machine knows not to break that down. Now, Veer seemed like an intelligent, interesting, engaging young person. But in fact, what he's made of is remarkably boring. He's 60% water, okay? Hydrogen and oxygen, and that's the same for all of you. He then, like everyone else, has a bit of fat. You've got to have some fat on your body in order to be healthy. And then we've got the other tissues, mainly made of proteins. We've got the connective tissues, bones, hair, skin, nails. And that brings us to 96% of the atoms that make up Veer, okay? It's carbon, nitrogen, oxygen, and hydrogen. Those 4 elements are the most common elements in the universe, and they're the most common elements in our body. And if we add just another couple, phosphorus and calcium, we're now up to 99% of Veer's atoms, okay? So 99% of our body's made of just 6 elements. We've then got a few what we call trace elements. So we've got about 100 grams of potassium, sodium, chlorine, sulfur, and magnesium's about 50 grams. And then we're down to pretty small amounts. So all of your bodies contain about 1 nail's worth of iron, about 5 grams. Zinc, you've got about 2 grams. Copper, you've got 1/10 of a gram. And then we've got some other elements in very, very small amounts. Manganese, selenium, iodine, fluorine, chromium, and molybdenum. And these, you could put all of them in a little salt shaker. Here you go. Can you see that tiny amount of molybdenum right there? Of course you can't. It's less than 1/100th of a gram. But without that, you can't survive. There are probably other elements in even smaller amounts, like cobalt, that we definitely need to survive. And we know remarkably little about them. But the really important thing to say is there is a correct amount of all of them. There's like a Goldilocks amount. We all know that iron is good for us, right? We're told that the whole time. It's in our breakfast cereal. Iron is important in your body. It carries oxygen around your bloodstream. It's also the stuff that turns your snot green. It's in the enzyme called myeloperoxidase, which kills bugs in your snot. But too much iron, whether it's because you've eaten too much or you have a genetic condition, can give you something called hemochromatosis, which, if it's untreated, can be really, really dangerous. So we somehow need to eat the exact right amount of all of these different elements from our diet. OK, I think it is time to reconstruct Veer. I've never done this before. I don't know if we can run the machine in reverse, but he seemed like a nice chap, so I think it's worth giving it a go. Let's put Veer's ingredients back in the machine. Are you ready? Hit the button. 1, 2, 3, 4, 5. He's back! Oh, with their glasses upside down. You've been a very good sport. How are you feeling? A bit tired after that ordeal?
A bit dizzy.
A bit dizzy. Well, it might be because I forgot to put one of the nails back, so you're probably quite iron deficient. So take that back to your seat and Veer, big round of applause. Thanks for being such a good sport. Where are you up there? So that's the atoms, the elements, but what about the molecules? Because our body is an amazing chemical factory. There are hundreds of thousands of unique molecules throughout our body, and we can make from scratch almost all of them. But there are just a small number that we do have to eat. There are 24 of them. 2 of them are called essential fatty acids, alpha-linoleic acid and linoleic acid. You've got to eat them in very small amounts. You get them from plant oils. There are 9 amino acids, which you get when you eat protein from plants or animals. And then there are 13 vitamins. And they've got to explain what a vitamin is. It's an organic molecule that you need for your cells to function that you can't make. And for almost all of those vitamins and the fatty acids, again, there's a Goldilocks amount. You have to eat not too much and not too little. Vitamin A, particularly, too much is very poisonous. Too little is equally fatal. So how do animals do this? We're quite used to reading dosages on the side of our vitamin pill bottles, but animals don't do this, and clearly we didn't have vitamin pill bottles for most of our history. Well, carnivores have a pretty easy job, OK? The lion is made of the same ingredients as the giraffe. All of the vitamins, the essential fatty acids, the minerals in the giraffe that the lion needs, it can just get by eating raw giraffe and building itself. But herbivores have a much harder task because plants, fungi, algae, they are made of quite different things. And so somehow herbivores have to move through the world, avoiding the carnivores and eating not too much and not too little of all of those different vitamins and minerals. How do they do it? And can humans do the same thing? Well, the first person to really try and answer this scientifically was an American pediatrician called Clara Davis. And she was doing this experiment almost 100 years ago in Chicago in America. And there was a problem at the time that lots of people had babies that they couldn't afford to look after. And so Clara Davis admitted these very young children, some of them were babies, some of them were toddlers, admitted them into a ward where they lived, and she started doing a very long-running nutritional experiment. And she wanted to answer this question: could very young children maintain nutritional health by choosing food for themselves? And so at every meal, they got little dishes like this. They got 32 different foods in total. And some of these things will be really familiar to you. There's some porridge oats, there's some salt, there's a raw egg. They had raw egg, they had milk, they had bone marrow jelly, okay? They also had banana. These are real calf brains. Dylan, Thomas, do you want some real calf brains?
No, thank you.
Sure, okay. And all of the kids were given salt in a separate dish. They could eat as much as they want. And this stuff, which is cod liver oil. And the important thing you have to know is that cod liver oil was at the time really the only good source of edible vitamin D, okay? This experiment, which she ran for a long time, has never been repeated for ethical reasons. You can't lock children up and, you know, give them limited access to food and make them choose their own food. But I would not be held back by such petty ethical concerns. So I got hold of a baby earlier this week and did the experiment at small scale. This is the baby I got here in the RI library. This, of course, is my own daughter, Indigo. She's 9 months old. And there's lots of food she hasn't tried. So we tested her on the salt and we tested her on the cod liver oil. So we give her a bowl of salt and she's got salt receptors in her mouth. There's a lot of noise always at dinner times. We are not making her eat it. She's choosing to eat it and she's going to choose the amount. And Indigo puts some in her mouth, doesn't mind it at first, and then she slightly overdoes it and retches a bit. None of the children in the study over many years, none of them ever developed either a deficiency of sodium or an excess of sodium. Salt can be very, very dangerous for babies if they have too much of it. So then we tried Indigo on the, this is a lovely frame to pause on the cod liver oil, and something about that, she's reaching for it immediately. Now, she's not very coordinated, her motor skills aren't good. And so the crying there, I think, is frustration. She just wants to get at it. She has a taste, cries, and then reaches back for it, grabs it back from my wife, Dinah, and enthusiastically drinks the rest of the cod liver oil. Now, many children were admitted to the experiment, and they all had access to all of the foods, and they all ate, throughout the experiment, almost all of these foods. They liked them all. But there was only one child. They all tried the cod liver oil, but only one child went back to it. And the child's name was Earl. And we have a picture of Earl here. This is Earl at 9.5 months. And you can see he's not a happy-looking kid. He was admitted with a disease called rickets, which is vitamin D deficiency. And when you lack vitamin D, you can't lay down calcium and phosphorus in your bones. You get weak bones. We can see here an X-ray. This is when he was admitted. You can see the bones are fuzzy. They're not very white compared to the arms, okay? There's not a lot of mineral in the bones. So Earl is admitted with vitamin D deficiency rickets, and he's offered the cod liver oil like all the other kids, and every single day, he, like Indigo, chugs that little glass of cod liver oil. He loves it. He drinks a lot of it. It's quite a big glass he has. And gradually, his rickets get fixed. So if we see the next X-ray, this is after about 5 months of drinking cod liver oil. You can see his bones, very, very crisp, clear ends. They're bright white, and his calcium and phosphorus levels have normalised in his blood. And on that day, he stopped drinking the cod liver oil and never touched it again. Something in him was telling him he needed something in that cod liver oil. And we still don't understand very much about what it was that he was tasting. And the really interesting thing for me was I assume that Indigo is getting enough vitamin D in her diet, but her enthusiasm for cod liver oil makes Dinah and I wonder if we should be thinking a bit more carefully about what she's eating. And here is Earl looking incredibly healthy a few months later after his rickets has been cured. So clearly, humans and wild animals, without any access to dosages or nutritional information tables, are able to meet their nutritional needs perfectly. You don't have to calculate the amount of sodium in all your food to not become sodium deficient or to not become excessive in sodium. But one of the other things that wild animals and humans historically regulate very, very tightly is the amount of energy we take in. We've historically not put a lot of energy into storage on our bodies. But in the UK now and around the world, that is changing. We seem to have stopped being able to regulate that energy store on our bodies, mainly in the form of fat, and so we are all getting larger. And this has caused a controversy in science because two things seem to have changed at the same time. First of all, the food we eat has dramatically altered. But the other thing that's really altered is how we live our lives. We're all much more sedentary. We do less. So are we getting larger because of our lifestyle or are we getting larger because of our food? Well, to demonstrate the answer to this, I am going to need 4 more volunteers to play me. Okay, I'm going to go up to the back, the young person in the, you've got reindeers on your top there. Okay, we'll have both reindeers, yes, since you stood up to the left of the boy with the Arsenal top. Yes, you. Great, come on now. Let's also get you and you as well. Come on now. Stand in a line here. Now, you're all being me. What's your name?
Boris.
No, you're Chris. Remember? Okay, name?
Chris.
Very good. Chris. And Chris. But you are different versions of Chris. The important thing is you're all 46-year-old men. You weigh around 80 kilograms, okay? And you have a small amount of male pattern baldness, but not any amount that we're going to draw attention to. Okay, but you have very different lifestyles, okay? So you, Chris, you are an ancient hunter-gatherer. Can you put that around your neck? Okay, so you live, Chris, 50,000 years ago, before the dawn of agriculture. If you want to eat meat, you have to chase down an antelope, okay? You run about 15 kilometers every day. If you want to eat vegetables, you've got to climb a tree or dig them out of the ground with a stick, okay? You have an incredibly active life. Got that? Everyone got that? Right. Now, you are Dr. Chris, okay? So you're not entirely sedentary. You walk around the hospital a bit. You cycle to work once a week, but you are not brilliantly active. You don't have a gym... Actually, you do have a gym membership and you never go. You don't have time for exercise. You are pretty busy being a doctor. You don't do nothing, but you're not being like the hunter-gatherer. Now, you... What's your name?
Helena.
No, you're not. You're Chris.
Chris.
You're PE teacher, Chris, okay? I would have loved to have been a PE teacher, and you have a very, very busy life. Okay, you do have a gym membership, you go about twice a week, and you spend a lot of your time running around with kids, helping them keep fit. And finally, we have professional gamer Chris. Okay, this version in my life, I got a job at a fancy gaming company and I test and develop computer games. I sit all day at a console. It's a great job, you're making loads of money, but you have no time for exercise. You don't get a lunch break, you drive to work in your sports car. Okay, 4 different Chris's, and now we are going to play a game of more or less energy. Now, in this game, it's a very simple game. There's a lot at stake. You're all going to play as one team together, okay? And if you can get 2 out of the 4 questions right, everyone in this room will go home with their own individual luxury yacht. Okay, the yachts are all out there, ready to go. All right, so the game is more or less. We're going to start down here, and I'm going to ask you a question, and you just have to all shout more or less. Does hunter-gatherer Chris burn more energy running for 15 kilometers a day than Dr. Chris? More or less? More. Okay, great. So hunter-gatherer Chris, can you come here, swap places? We're going to move you up here. Does hunter-gatherer Chris burn more or less energy than PE teacher Chris? More. That was very... I thought someone might say less, but I think that's right. You know, PE teacher Chris is running around a bit, but you don't ever have to chase game down, do you? Okay, great. So hunter-gatherer Chris is going to move this way. And... is hunter-gatherer running down antelope all day, every day, digging tubers out of the ground Chris, burning more or less energy than sedentary gamer Chris? Thank you. So, do this. Now, is sedentary gamer Chris burning more or less energy than Dr. Chris? Less. Less. Very uniform. Okay, so there Who thinks that PE teacher Chris burning more or less energy per day than Dr. Chris? Okay, let's move you there. Okay, well, let's start with Dr. Chris. You're wearing an envelope that will say the amount, approximately, that someone of my size and build and age and sex would burn every day, 2,500 kilocalories. Great. Now, let's go to PE teacher Chris. Let's see how much energy. There's a lot riding on this. 2,500 calories per day. Okay, so you've got one wrong. These two were the same, and no one said that. Let's go to Gamer Chris next. Open your envelope. What's it going to say? 2,500 calories per day. So these three seem to be burning the same amount of energy per day. Finally, Hunter-Gatherer Chris, surely you are going to be using more energy every day, but you're not. 2,500 calories per day. The best science, and this has been done on humans and animals, shows us that people with the same body composition of the same age and the same sex, regardless of their lifestyle, burn around the same amount of energy per day. There are some extreme exceptions. If we had an Olympic athlete, an Arctic explorer, they might be an outlier. But within these four groups, we have evidence that they're burning very, very close to the same amount of energy per day. Now, this challenges everything we've all learned about the way energy works. It seems to challenge everything I've said so far in this lecture. Well, to help us understand what's going on, I want to say goodbye to Dr. Chris and Hunter-Gatherer Chris and give you a big round of applause, but I want PE teacher Chris and Gamer Chris to stay behind. So a big round of applause for you two. So we want to demonstrate what's going to happen now. So I've asked Dan to prepare a very, very straightforward, safe and simple demonstration of energy use to talk about the similarities and differences between Gamer Chris and PE teacher Chris. Dan, what have you prepared for us in the tubes?
Gunpowder.
Gunpowder, great. But not real gunpowder.
Real gunpowder.
Real gunpowder,
Yeah.
OK.
Yeah.
But we're not going to let the kids set it off or anything.
Well, I'm not doing it.
The kids are going to set
Oh,
it off.
yeah.
OK, brilliant. This is the absolute last thing I wanted. Clearly, it's very important you don't do anything with gunpowder at home. Now, a lot of your energy just goes on cellular metabolism, keeping your cells churning over, keeping your heart pumping, your breathing muscles working, your immune system functioning. Your brain requires a massive amount of daily energy, no matter what else you do. So you're committed to spending around half your energy budget on that stuff. So Dan, how are we going to do it?
OK, so if you pop those goggles on in front of you there, pop these goggles on as well. OK. In a moment, I'm going to give you a remote. You, my friend, are going to press button A. You've just got one button to press in a moment, OK? So let me arm that. Hold on to that. Take a big step back. Don't press the budget. Step back. Let me arm this one. Take a big step back. Remember, we'll do a countdown, and you're going to hit your buttons. You're hitting that button. You're hitting A. Chris, you might want to step back a bit. OK, should we give them a countdown? 3, 2, 1.
Brilliant. So this is the energy that's just being used in the body to maintain functions, to build and repair tissues, to run the immune system. If you spent all day asleep, you would still be having to use this energy. You're committed to it. But now we have some differences. So I'm going to go first of all to Gamer Chris, because you've each got around half your energy left.
Yep,
so
we've got some energy left.
You've got a little canister of gun. It's great, we're just getting the kids to handle the gunpowder. Love this. So, Gamer Chris, you're going to come forward, and Dan has set up some more tubes.
So
now, remember, Gamer Chris is committed to spending the energy. He's not going to store this excess energy, all right? He's going to burn it. The question is, what are you going to burn it on? Well, we have 3 tubes here that represent, Dan, put out the signs.
So we're going to represent stress, inflammation, and other things.
And other things, OK? So I want you to pour some gunpowder. Dan will give you a hand. And Gamer Chris, remember, doesn't have any choice here. And the grown-ups will recognise this in the audience. We end up in a life that's sort of handed to us by lots of external forces. So this isn't some deficiency of Gamer Chris. He hasn't made bad choices. He's ended up with a job in a life where he cannot choose to go and spend this energy on doing exercise like PE teacher Chris can. OK. Are these armed? Is that the right expression?
They're now armed. OK, we'll give you a countdown again. Are we ready?
3, 2, 1. Amazing. So what's happening here is levels of inflammation are up, we're spending energy on anxiety, we're spending energy on high hormone levels that actually aren't very good for us. Gamer Chris, how are you feeling now?
I'm feeling like not very active.
Yeah,
Not doing much and like very like empty now that I've burnt all my energy.
yeah, and a bit sore, a bit tired, a bit generally unwell, possibly a bit unhappy. Well, I think you should get off your bus or stop early on the way to work. Speak to your line manager, see if you can get a long lunch break and go to the gym. But Gamer Chris, thank you very much for demonstrating that. Brilliant demonstration. Head back to your seat. Now we have PE teacher Chris. Now, how are you going to spend your days?
Going to the gym, exercise.
Right, you've got to take year 1 to do a bleep test. Is that the kind of thing you do?
Mainly we just use terrible resources to play sports.
OK, PE teacher Chris. Now, Dan, talk us through what PE teacher Chris is going to do here.
So I have another tube. If you could come and pour all of your powder into there. Let's see if we can do it without the funnel. Go on, going that way. Just gently, gently. There we go. Tap, 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 tap. So could you just hold that device for me?
So, Dan, you are now actually making an explosive.
Yes.
So PE teacher Chris is going to use all their energy pretty quickly during the day to do all the exercise that their job requires of them.
Then we get to bring on something really cool. Bring on the bomb tank!
Ear defenders, can we...
We're going to put the ear defenders on. We're going to go put it in there. Lower it down through the middle. And then we're all going to back off over this way, please. Because over here, we have my other really cool toy.
Mm-hmm.
I'm scared at this point.
You're scared? Don't worry, because we have the big red button.
Yeah, nothing to be scared of there.
Nothing to be scared of there. So, we're going to give a countdown, and you're going to press that big red button. Ready? 3, 2, 1.
And big round of applause for PE teacher Chris. How are you feeling now? You're going to go straight to bed. Yeah. You're not going to spend any energy on anxiety. Now, there's a theory we've demonstrated there, which is why we think exercise is good for us. And there's a lot of evidence in agreement about this, not a lot of evidence to the contrary, but it's still a theory. We think that exercise is good for us because it steals some energy from our budgets for inflammation and for anxiety. But what it isn't doing is changing the total amount of energy that you're burning in a day. The evidence about weight gain is, in my opinion, extremely clear. The reason that we are getting larger as a species is because of the food that we now eat. And that is going to be the subject of my next lecture. But I want to leave you with one final thought. This plant that I showed you earlier, you've all been losing weight throughout this lecture. And where does weight go when we lose it? We breathe it out. You've taken carbon atoms from your fat stools, from your sugar stools, and you've breathed them out into the air. This plant will have taken atoms from every single person in this room, and it will have absorbed them, and it will have, over the course of the lecture, started to use those atoms from each and every one of you to build those macronutrients and those vitamins, those complex molecules that we all depend on for survival. This is the carbon cycle, which links all life on Earth together and on which all life depends. So thank you all very much for listening.